Sir Isaac Newton gave us a mathematical framework that can, in theory, predict the exact motion of any object in the universe. The core mechanism of his laws requires identifying every specific force vector acting on an object and calculating the resulting acceleration, updating those calculations fraction of a second by fraction of a second. Look at this diagram. We have a standard mechanics problem, a mass on a table, m1, attached to a spring, pulled by a string connected to a hanging mass, m2, over a pulley. When we let the system go, gravity pulls down on the hanging mass, creating tension in the string that drags m1 across the horizontal surface. But there is a major complication. As m1 moves forward, the spring stretches. According to Hooke's law, the spring fights back, and that counterforce increases constantly the further it gets pulled. To calculate the motion of this block using Newton's laws, we would have to recalculate the exact force and acceleration vectors for every single millimeter it moves. Tracking thousands of shifting directional vectors in real time creates an immense computational load. It is incredibly tedious and highly susceptible to calculation errors. Force equals mass times acceleration is true, but for complex, continuous motion, it becomes an inefficient tool. We need a completely different analytical lens to evaluate the motion. Physicists bypass the gridlock of continuous vector tracking by using the work-energy theorem. This approach shifts our focus away from tracking spatial trajectories. Instead of managing the direction of every interacting force, we audit a single numerical value, the system's total energy. To use this method, the absolute first step is to draw a rigid conceptual boundary around exactly what we are analyzing. This text outlines the physical definition of a system. It defines it simply as a specific, small portion of the universe that we isolate for study. The observer chooses the boundaries. A valid system can be a single particle, a massive collection of objects, a fixed region of space, or a physical shape that deforms over time. Once that boundary is established, literally everything else in the universe is classified as the environment. This brings us to the physical definition of work. Work is strictly the measurable transfer of energy that crosses the boundary between the environment and our defined system. By setting a rigid boundary, we can ignore the chaotic internal force vectors. We replace them with a straightforward scalar audit of the energy entering or leaving our designated zone. Calculating that energy transfer presents a mathematical hurdle. Forces are rarely applied in the exact direction that an object actually travels. This diagram illustrates a common directional mismatch. Here, a woman is pulling a heavy block across the floor using a rope. Because she pulls upward at an angle, only a specific fraction of her physical effort actually contributes to moving the block horizontally forward. This is a geometric diagram of two general vectors, A and B. Physics uses this pure vector mathematics to handle directional mismatches universally. To find exactly how much of one vector works in the direction of another, we use a specific operation called the scalar product, commonly known as the dot product. The geometry here involves mathematically projecting vector B down onto vector A, creating a right angle, to isolate exactly how much the two vectors overlap. The resulting equation multiplies the full magnitude of A by the parallel magnitude of B. We write this as A times B times the cosine of the angle between them. This leads to strict physical limits. If a force acts completely perpendicular to the direction of motion, the angle is 90 degrees. The cosine of 90 is 0, meaning absolutely zero work is done. Conversely, if a force pushes directly against the motion, the work done is negative. Energy is actively drained out of the system. The dot product acts as a rigid mechanical filter. It discards the useless angles and extracts only the parallel components of two interacting variables. In reality, objects move in 3 dimensions, making it incredibly difficult to measure a single clean angle between force and displacement vectors. This diagram shows the standard Cartesian 3D coordinate model, mapping space along the x, y, and z axes, each with their respective unit vectors, I hat, j hat, and k hat. These unit vectors have a magnitude of exactly 1. Their sole mathematical purpose is to assign a strict direction along those geometric grid lines. This slide details the algebraic rules when we apply the dot product directly to these unit vectors. When multiplying matching directions like I hat dot I hat, the vectors are perfectly parallel. They multiply cleanly to equal 1. We use the term orthogonal to describe dimensions that are perfectly perpendicular to each other in 3D space, like the x and y axes. Because orthogonal axes sit at exactly 90 degrees, their dot product is 0. This creates an efficient shortcut for complex 3D math. Mismatched orthogonal pairs vanish entirely, leaving only the cleanly matched x, y, and z components. Applying this to raw data, if a force vector of 20 I hat minus 10 j hat acts over a displacement of 5 I hat minus 4 j hat, we simply multiply the matched pairs. 20 times 5 plus negative 10 times negative 4 yields exactly 140 joules of work. Unit vector multiplication operates like a mathematical sieve. It instantly converts highly complex 3D directional coordinates into a single clean scalar value. We can now apply this dot product logic back to our initial diagram of the poled block. We have a constant force of 100 newtons being applied over a horizontal displacement of 5 meters. The angle of intersection between her pole and the floor is exactly 37 degrees. The calculation is straightforward. 100 newtons times 5 meters times the cosine of 37 degrees. The vertical components strip away, leaving us with exactly 400 joules of work. For any constant force, the dot product provides an immediate, foolproof audit of the total energy transferred into the system. But we still have to resolve the primary real-world complication we noticed earlier. Physical forces are rarely perfectly constant. Look at this diagram showing a block attached to a stretched spring at position X. As the block is pulled further outward, the spring fights back with a progressively greater counterforce. A simple multiplication of force times distance fails here, because there is no single constant force value to plug into the equation. This chart maps that continuous change. We plot the varying force on the y-axis against the changing position on the x-axis, creating this distinct trapezoidal shape. The graph shows the force increasing steadily, holding at a constant level for a specific duration, and then steadily decreasing back to 0. Because our axes are force and displacement, the product of any vertical segment and its horizontal width represents a specific amount of work. Summing these segments across the total distance reveals that the work done is exactly equal to the area bounded beneath that line. By calculating this internal area, whether using basic geometric formulas for a shape like this, or integral calculus for complex curves, we extract the exact scalar energy transfer. By defining clear boundaries and using scalar tools like the dot product, the work energy theorem converts complex 3D motion into a manageable energy audit. It replaces the infinite recalculations of Newtonian vectors with a single calculation of energy transfer.